Hey everyone, and welcome to this explainer brought to you by Forge College. We are continuing right along in our Solidity from Zero track. If you've been following us, you know we've been working hard to build a really rock-solid foundation. Well, today is a fun one. We're diving into function modifiers in Solidity. Think of this as the exact moment we graduate from just writing functional code to actually adding real security so our smart contracts don't get completely drained the second they go live. Let's dive right in.
All right, here's our blueprint for today. We'll cover 1. What are modifiers? 2. The mechanics and basic syntax. 3. The magic placeholder. 4. Bouncers and middleware. And finally, 5. Best practices and trade-offs.
So before we introduce the solution, we kind of need to establish the problem, right? In our last explainer on best practices and patterns, we worked really hard to make our functions clean, predictable, and perfectly scoped. We nailed down the visibility, handled storage beautifully, all that good stuff. But out there in the real world of Web3, functions need armor. We're talking access control, input validation, execution guards, the whole shebang. So the big question becomes, how on earth do we add all that robust security without totally ruining our pristine code with an ugly, repetitive mess of checks?
That brings us to Section 1. What exactly are function modifiers? Simply put, they're reusable wrappers for control flow.
Okay, let's look at the strict definition. A function modifier is a syntactic wrapper expanded at compile time to alter or guard the execution of a function. Now, let's break that down a bit because, literally, every single word there matters. First off, it's a wrapper, which just means it surrounds your existing function. It's syntactic, meaning it's a built-in structural tool in Solidity. And this is the absolutely crucial part. It expands at compile time. The compiler physically weaves this wrapping code around your function before it ever even hits the blockchain. This lets you check conditions before a function runs or validate state changes after it runs without ever cluttering up the main body of the function itself. Moving right along to Section 2, Mechanics and Basic Syntax. Let's look at the anatomy of a guard. Let's do a quick side-by-side comparison to really see this in action. On the left, we've got this completely naked, repetitive function. Every time it runs, it has to manually check if the caller is the owner using a require statement, and only then does it set the value. Now imagine having to write that exact same require statement on 50 different functions. It's an absolute nightmare for maintenance. But if you look over on the right, it's the exact same function, but now it's wearing this clean little modifier wrapper called onlyOwner. The function body itself is now hyper-focused on its one primary job, setting the value. The onlyOwner modifier handles all the access controls somewhere else. It's readable, it's modular, and honestly, it's just so much clearer. Section 3, the magic placeholder. This is all about the underscore semicolon switch. Now, if you're wondering how this actually works under the hood, it all comes down to a very specific mechanical injection point. This is our placeholder, the underscore semicolon. When you write a modifier, you typically put your pre-checks at the top, and then you just drop in this little placeholder. At compile time, the Solidity compiler takes your entire original function body and literally copy-pastes it exactly where that switch is located. It hands control from the modifier down into the function, and then, if there's more code, right back up again. It's a real game changer. To make that super concrete, let's walk through the exact chronological steps of how this executes. Step 1 is the pre-check. This is any code you wrote in the modifier before the placeholder. It always runs first, and usually this is where you check permissions or user balances. Step 2 is the placeholder itself. This is where your core function body actually executes. And then step 3 is the post-check. And yes, you can actually write code in a modifier that runs after the underscore semicolon. This code runs after your function finishes executing, which is amazing because it lets you validate that a state change happened correctly or even revert the entire transaction if the final outcome isn't what you expected. So let's just quickly summarize those core properties. Pre-checks are critical. They can revert a transaction early. This means they completely prevent the function body from executing, which saves you and your users valuable gas. Post-checks, like we just said, let you validate state changes after the main event. What's also super cool is that modifiers can take parameters, which makes them highly reusable across entirely different contexts. And finally, you can actually attach multiple modifiers to a single function. They just nest chronologically in the exact order you write them out. Which brings us to Section 4, Bouncers and Middleware. Let's build a couple of mental models for this execution logic. The best way to think about single modifiers for access control is to imagine a ridiculously tough bouncer guarding the door to an exclusive VIP club. When a caller tries to execute your function, they have to get past this bouncer first. As a smart contract engineer, your goal is to put your cheapest, easiest to fail identity checks at the very outermost door. If someone isn't the actual owner of the contract, Boot them out onto the curb immediately. Do it before the EVM spends expensive gas doing complex math. Modifiers act as these frontline bouncers, fiercely guarding the inner VIP section of your function body. But what about when we stack multiple modifiers? For that, let's use a middleware metaphor. Think of it like a nested assembly line. When a function has, say, 3 different modifiers attached to it, execution plunges inward. It hits the first modifier's pre-check, steps down into the second modifier's pre-check, and then down into the third. Finally, it reaches the core function body at the very center. Once the function wraps up, execution flows backwards. It ripples out through the post-checks of the third, the second, and then the first modifier. It's this incredibly elegant nested pipeline of logic. All right, Section 5, Best Practices and Tradeoffs. Knowing exactly when to wrap and when to just inline your code. We've got 4 golden rules for you when working with modifiers. 1. Use them for pure gating logic and role checks. If it's a simple yes or no permission check, wrap it, for sure. 2. Avoid hiding complex state mutations. If your modifier is quietly changing user balances or updating critical mappings in the background, stop right there. Complex state changes need to be highly visible inside the main function body so you don't confuse future maintainers or auditors with hidden math. 3. Document all side effects clearly. If a modifier does have to change state for some reason, scream it from the rooftops in your comments. And 4, parameterize for context-specific reusability. Please don't write 10 different modifiers for 10 different numerical limits. Just write one parameterized modifier that accepts the threshold limit as an argument. To wrap up that thought, I really want to leave you with this defining principle to anchor your whole engineering mindset. Treat modifiers as control flow constructs, not as substitutes for explicit, well-documented function behavior. Basically, they are traffic cops, not hidden factories. You want to keep your core behavior incredibly obvious and use modifiers strictly to safely direct the flow of that behavior. And that brings us to the end of today's explainer. We've unpacked the compiler mechanics, decoded the magic placeholders, and laid down some absolutely essential architectural best practices. So what's the next step? Well, we need to actually start enforcing these rules in real code, which is exactly what we'll tackle in our next lesson, access control and validation with modifiers. Thank you so much for joining me today on behalf of Forge College. To continue your journey in the Solidity from Zero track, be sure to head over to forge.college. But before you go, I want to leave you with a final thought to chew on. If you were hired to audit a high-stakes smart contract tomorrow, where would you look first to find hidden vulnerabilities? The functions themselves or the seemingly innocent modifiers guarding them? Think about it. See you in the next one.